In this video, we're going to be looking at topic 8C, which is the inorganic chemistry of group 7, and this is part of the IAS chemistry course offered by Edexcel, and this is unit 2. So we're going to be looking at the trends in group 7 for boiling temperatures, melting temperatures, physical state, electronegativity, and reactivity. We're going to be looking at in terms of redox reactions of our halide ions and aqueous solutions. We're also going to be looking at differences in oxidation numbers and looking at specific reactions of the halogens, as well as how to use what we know about these reactions and reactivities to make predictions about fluorine and astatine. So elements of group 7 are known as the halogens, and the ions that they form, or the salts that they form, are halides. So our halogens are the atoms and our halides are the ions. And in this topic, we're going to look at the properties of chlorine, bromine, and iodine. We can then use our knowledge of these in order to make predictions about the others. So if we have a look at the table below, we can see that we've got trends in our melting and boiling point, our state at room temperature, and also electronegativity. So as we go from the top of the group down to the bottom, we see a movement from gases to liquids to solids. So this tells us that our melting and boiling temperature are increasing. And we also see a decrease in the electronegativity. And we should be able to explain why this is the case. So all of our halogens are going to exist as diatomic molecules. So they will all exist as two atoms stuck together. And we know from topic 7 that the melting and boiling points of elements or any molecule is going to be dependent on their intermolecular forces, and in this case it's going to be their London forces. Of course, because it is the same element, they don't have permanent dipoles, and there's no hydrogen, so we don't have any hydrogen bonding. So it's simply due to the London forces, because that is linked to the number of electrons. So as we go down the group, we're going to see an increase in our temperatures, and this is because we are getting more electrons in our molecule. The more electrons we have, therefore the more London forces. The more London forces means that we have stronger intermolecular forces, so we require more energy to break the intermolecular bonds. And that means that we have higher melting points. Now, despite chlorine, bromine, and iodine all existing as different states of matter, so chlorine being a gas, bromine being a liquid, and iodine being a solid, they can all form gases at room temperature or just higher. And we call this vaporization, where we're going from our liquid to a gas state or our solid to a gas state. So we see vapors being formed, and we can see different colors of vapors depending on which one it is. So if we have the bromine, we tend to see brown or orange vapors, and if it is iodine, we see purple vapors. Now we also see a trend that the electronegativity is going to decrease as you go down the group. So we know that fluorine is the most electronegative element in the entire periodic table with an electronegativity of 4. But as we go down the group, we're seeing a decrease, and this is due to the fact that, again, we have larger elements. As we get larger elements, that means that we have more electron shells being added. And the more electron shells that we have, the more shielding we get from our outer electrons. So our outer electrons become less attracted to the nucleus, causing there to be a decrease in the electronegativity. This same explanation also explains the decreasing reactivity down the group. We want to have the halogens attracting electrons very closely so that they can be held closer to the nucleus and that only work when you have smaller anions. So your larger anions, like iodine, are not going to be as reactive because the electron that is being added to the outer shell is further away from the nucleus. Therefore, it is less reactive. Now, there are over 60 possible combinations when the halogens are reacting with metals in group 1 and group 2. Now, we've already covered group 1 and group 2 reactions when we were looking at topic 8b, but we're going to look at how they react with the halogens in a little bit more detail. So because we don't need to know all of the different combinations, what we do need to know are the general rules. So the most vigorous reactions are going to be between the most reactive elements. So that's going to be the elements that are at the top of group 7, such as fluorine and chlorine, and the bottom of groups 1 and 2, such as cesium or even francium. Now, all of the products that are formed are all white ionic solids. They are all involving an electron transfer to the halogen. So the halogen is gaining an electron, and because that is gaining an electron, of course, then the metal is losing an electron. So these are examples of redox reactions. And in this case, the halogen acts as the oxidizing agent because it itself is being reduced. The oxidation number of the halogen will always go from 0 to -1 because we're going from the uncombined element to the halide, and the oxidation number of the metal will go from 0 to either +1 or +2, depending on what group it is. Of course, we're coming from 0 because it is just the metal itself, and remember, uncombined elements have an oxidation number of 0. So you can see that we have an example of lithium reacting with chlorine to make lithium chloride. So my oxidation number of the lithium in this case is going to be +1, and of the chlorine is going to be -1. And when we react barium with bromine, the oxidation number of the barium is going to be +2, and the bromine is going to be -1. So now let's move on to look at the halide-halogen displacement reactions. So you'll have met a displacement reaction back in GCSE, but just a reminder if you can't remember, a displacement reaction happens when a more reactive halogen displaces or takes the place of a less reactive halogen from one of its compounds. And we see usually happening in an aqueous solution so that we can see a colour change and we can actually see the displacement taking place. So just a reminder, it's going to be chlorine, bromine and iodine with your reactivity decreasing down the group. Now, due to differences in concentration and similarity of the colours, sometimes it can be quite difficult to actually see the change, and I'll show you a diagram in just a moment. So what we sometimes do in order to get around this is we add in an organic solvent, usually something like cyclohexane, and then that's added and shaken with the water. Now, cyclohexane and water don't mix. So what they do is they then form layers. And in order to, when we do this shaking, that is in order to make the halogen dissolve into the organic upper layer. And this actually allows the colour difference to be much clearer so we can see it much easier. So if we look at the reaction here, we can see that the bottom layer, this is going to be the aqueous layer, and you can see the three colours. Whilst there are some differences, particularly between the second and the third one, these are quite difficult to see. Whereas when you look at the organic layer, it is much clearer which one is which. So the first test tube is going to be the chlorine, the second test tube is the bromine, and the iodine is the third test tube, and the iodine is the one that is very, very easy to see, and you can see it is a very deep purple colour. This is a typical question in an exam, so make sure that you can name an organic solvent, cyclohexane probably being the best one, and make sure you know the colours of each of them. So we have green for the chlorine, orange for the bromine, and purple for the iodine. Now, all of these reactions are all examples of redox reactions. So the halogen is changing from 0 to -1, and the halide oxidation number is changing from -1 to 0. So chlorine being the most reactive is because it's due to a small atom and we're getting that attraction of the electrons more, so we're getting that higher electronegativity. So the chlorine can displace the bromine and the iodine. Bromine will only displace iodine, and iodine cannot displace either of them. Now, chlorine is also a special element in the fact that it can undergo a disproportionation reaction. So a reminder, a disproportionation is when you have the same species being simultaneously oxidized and reduced. So what you should see is you should see a species or an element appearing in two products. So for example, we can see in this reaction of chlorine with water, the chlorine appears in both of my products. And there are three key examples that you have to know for chlorine, and you should be able to write the full equation, give some information about the conditions, so does it need to be heated, what are the reagents, and also be able to show which one is being oxidized and which one is being reduced. So when we have chlorine reacting with water, we're going to form a mixture of two different acids. We make hydrochloric acid, which is HCl, the one that you're probably more familiar with, and we also make chloric 1 acid, sometimes known as hypochlorous acid. Now, to form the HCl, the chlorine is reduced to an oxidation number of -1, and to form the HClO, the chlorine is oxidized to +1. So remember, your oxidation number for chlorine gas is going to be 0, and then we're going to get -1 for the HCl and +1 for the HClO. So a disproportionation where we get both the oxidation and reduction happening. Now, you also need to know the reaction of chlorine with alkali, and there are two different reactions that we have depending on if we have cold alkali or hot alkali. If it's with cold alkali, specifically sodium hydroxide, then we're going to make two salts. We're going to make sodium chloride and sodium chlorate 1. So the sodium chlorate 1, remember the Roman numeral is going to tell us the oxidation number of my chlorine in this case. So it goes from 0 when it is a chlorine gas, and when it is in NaCl, the oxidation number is -1, and when it is in NaClO, the oxidation number is +1. And sodium chlorate is typically used as a disinfectant, and sometimes you might find it in bleach as well. Now, when we react it with hot alkali, you can see that we make a slightly different compound where we still make the NaCl, but this time we make sodium chlorate 5 or NaClO3. So in terms of the oxidation numbers, chlorine gas is 0. The NaCl hasn't changed, that's still -1, but when it's NaClO3, we have an oxidation number of +5. So again, chlorine being oxidized and reduced, but depending on whether it's cold or hot alkali, you will make two separate products. And sodium chlorate 5 is a weed killer, but it can also be found in bleach. Now let's look at the reaction of the halides specifically with sulfuric acid. Now, it's important that we can distinguish between the halides and the halogens. Halogens will act as oxidizing agents, so they will cause something else to be oxidized. The difference here is a halide ion is going to react as a reducing agent. So that means, remember, it reduces something else and it is oxidized itself. So if it reduces something else, it causes that other thing to gain electrons, and it does that by losing its own electrons or being oxidized. And the general equation that we can write here is we can show here where X is being our halogen, and we have two halide ions forming the diatomic halogen molecule plus 2 electrons. So we're getting this oxidation reaction happening. And the reducing power of the halides is going to increase as we go down the group. So as we go from fluorine to chlorine to bromine, from fluoride to chloride to bromide to iodide, we are going to see the reducing power increasing, meaning we're going to see the different products being formed depending on how strongly the halide is working as a reducing agent. Now, sulfuric acid can be partially ionized when it is concentrated. That just means that it splits down into its two ions. So we have H2SO4 can split to a hydrogen ion and an HSO4 ion, and that HSO4 can then be further ionized into another hydrogen ion and a sulfate. When it is concentrated, sulfuric acid will work as not only as an acid, but also as an oxidizing agent. So if we have the halide acting as a reducing agent and the sulfuric acid acting as an oxidizing agent, we can get a redox reaction happening here. And when sulfuric acid is reduced, there are 3 possible products, and it all depends on the extent of the reaction. So this just means it really depends on what reducing agent is being used and how much it is being reduced. And the 3 products are sulfur dioxide, or SO2, sulfur, or hydrogen sulfide, which is H2S. Now, depending on the extent of the reduction, you should then know 3 different half equations. And you can see that we have the half equations here. I would strongly suggest that you memorize these, or you can formulate the half equations. So in sulfuric acid, our oxidation number of the sulfur is going to be +6. And depending on how much it is reduced will depend on how much the oxidation number changes. So you can see that when it is slightly reduced to make SO4, the oxidation number changes from +6 to +2. So you get a change in oxidation number of 2. If it is being further reduced and we're going from sulfuric acid to sulfur, you can see it goes from +6 to 0, we're getting a change in oxidation number of 6. And as it goes that step further and goes from the sulfuric acid at +6 to hydrogen sulfide, which is an oxidation number of -2, we're getting a change in oxidation number by a factor of 8. And the number of hydrogen ions and the number of electrons in the equation is showing the same as this decrease in oxidation number. So you can see when we change by 2, I have 2 hydrogen ions and 2 electrons. And the change of 6 hydrogen ions, 6 electrons, and for 8 hydrogen ions and 8 electrons. So that's giving us the extent of the reduction. So 1 being a small extent and half equation 3 being reduced to a large extent. So what that must mean is that when we have specific halides, we're going to see a different level of reduction happening. So we're going to get different products being formed. So when we have a reaction with NaCl, we form one product of hydrogen chloride and we observe misty fumes. And we'll talk a little bit more in detail about this in just a minute. This is just a summary table. When you have sodium bromide, you're going to see 3 different observations. You're going to get some misty fumes due to the formation of hydrogen bromide. You're going to get some brown fumes due to the formation of bromine. And you're going to see a colourless gas with a choking smell, and that's your sulfur dioxide. So if I just go back one slide, that's showing that we're getting this half equation 1 happening. When you have the reaction with sodium iodide, we see 5 different products being formed. So we get misty fumes for hydrogen iodide, we get purple fumes or a black solid, and that tells us that we've formed iodine. And we also see all 3 of our reduction products from the sulfuric acid. So the colourless gas with choking smell is your sulfur dioxide. We see a yellow solid, which is the sulfur, and the colourless gas with the rotten egg smell is hydrogen sulfide. So when we have iodine or iodide, we are seeing all 3 of these half equations happening because it is much more reducing than the others. So let's break each of these down into a little bit more detail. So when we react the sodium chloride with the sulfuric acid, here the acid is only acting as a base, so we don't get any redox reaction occurring. Actually, the chloride, because it has a low reducing power, here it's not even using its reducing power, it is actually acting as a base. And we get the formation of the NaHSO4 and our hydrogen chloride. And remember, the hydrogen chloride is what's going to give us our misty fumes. Now, when we react the sodium bromide with the H2SO4, we're still going to have it acting as an acid to form our hydrogen bromide. However, this hydrogen bromide then acts as a reducing agent in order to form the bromine and the SO2. So this top equation is where the bromide acts as a base. Okay, and it is when it is in the sodium bromide. We're reacting and we're getting a similar equation that we see with the chloride. The HBr that is formed here are your misty fumes, but then that HBr then can undergo a redox reaction, and in this case we have the bromide and the hydrogen ion from the HBr reacting in these redox equations in order to form our bromine as a product and our SO2, and we can combine those half equations to give us this overall equation here. So we're having the bromide acting as 2 different substances, acting as a base and acting as a reducing agent, and we have the H2SO4 acting as an acid and an oxidizing agent, just depending on which part of the reaction is taking place. Now we see a similar thing with the sodium iodide, that should say, and in this case we get the acting as a base here with the iodide forming my HI, and then this hydrogen iodide can then undergo a redox reaction, so breaking down into the iodide and the hydrogen, and we can form our SO2, our sulfur, and our H2S product. So this is always going to be the reaction of the iodide. And you should be able to write out ionic equations for each of the different products that are formed. So we've seen the change to make the SO2 on the previous slide. Now we're seeing the change to make the sulfur. So we get a combination of this equation, and you should be able to determine the equation for the oxidation of the hydrogen iodide to form the H2S. That's when you're reacting it with 8 hydrogen ions, so our H2SO4 with 8 hydrogen ions and 8 electrons in order to form the 4 waters and H2S. So if I combine these 2 equations together, I'm going to have to multiply the top one by 4 to give me my electrons cancelling out. So I'm going to have 8 hydrogen iodides plus H2SO4 to give me 4 waters plus the hydrogen sulfide plus 4 iodine molecules. and that would be the ionic equation to show the further reaction to form the hydrogen sulfide. So you should be able to write out using these three half equations. You should be able to write them out to show how each of the halides act as a reducing agent and be able to summarize the products in this table to show their formation. It is very important that you can write the equations, the names of the products, as well as the observations. All three of these are key for you to be able to answer questions. This comes up very regularly in exams. Now, other reactions of halides are ones that you've seen before. So using back in IGCSE when you did chemical tests, we can identify that a halide ion is present due to the formation of a silver halide compound, and taking into account the fact that they have a low solubility, we can form precipitates. Okay, so we get that white, cream, and yellow precipitates. But because these are quite difficult sometimes to distinguish between, what we can actually do then is we can take advantage of the fact that they then all have different solubilities in aqueous ammonia, and we can easily distinguish between a chloride, a bromide, and an iodide. So how this happens is we add the dilute nitric acid to our suspected halide compound, and this just removes any other precipitates. We add the silver nitrate, and this is to form the precipitate, and then we add the aqueous ammonia, and it can either be dilute or concentrated depending on which one it is that you want to test for, and then we observe does the precipitate dissolve or does it stay. And what we should see is the following. So when we add the silver nitrate solution, for chloride we see a white precipitate, bromide, we see a cream precipitate, and iodide, we see a yellow. Now, if you look at tubes 1, 3, and 5, you can see that these are quite difficult to actually determine the different colours, especially 1 and 3. So 1, 3, and 5 are your tubes to show what's happened when you've added the silver nitrate solution. So this is 1, 3, and 5. Now, we can then use the solubility in ammonia to tell us the difference between these three so that we're not using our subjective colours. Now, regardless of if it is dilute or concentrated, chloride ions are going to be soluble. So if you make a precipitate that you think looks white but you're not 100% sure, you can add in some dilute aqueous ammonia, and if the precipitate dissolves, then you know you have chlorine. And that's what we see in test tube 2 here. So this is the addition of the precipitate, and we're seeing, the addition of the aqueous ammonia, and we're seeing the precipitate being removed. If we add dilute aqueous ammonia to bromide ions, it is not going to dissolve. Okay, so what we would do is we would then add concentrated aqueous ammonia, and what we would see is that it does dissolve in the concentrated but not the dilute. And that's what we see in number 4 here. So this is going to be my chloride, and this is going to be my bromide. So this is an only concentrated aqueous ammonia. And for the iodide, usually the iodide is quite easy to see because it is quite yellow, but we always just double check. And what we see if we add dilute or concentrated is that both are insoluble. And that's what we see in test tube 6. So this is our iodide. So you will have learned in GCSE the silver nitrate test with the different precipitate colours. The extension at A level is the aqueous ammonia. So you should always be referring to doing the silver nitrate test and then the aqueous ammonia in order to tell us, does it dissolve or not? So the general equation for the formation is going to be your silver ion reacting with your halide ion to form your silver halide precipitate. And then the dissolving of that precipitate in the aqueous ammonia distinguishes between the colours. And in this case, it's going to form something called a complex ion. Now, you will learn more about these in topic 17 of year 13. But what you can see is that we have the silver, in this case silver chloride, reacting with the ammonia, and the ammonia is going to take the place of the silver, take the place of the chloride and react with the silver, and we liberate the chloride ions. Now, hydrogen halides can also react with water, and they're going to form colourless acidic solutions. So we have hydrogen fluoride forming hydrofluoric acid, hydrogen chloride forming hydrochloric acid, hydrogen bromide forming hydrobromic acid, and hydrogen iodide forming hydroiodic acid. And you can see that we have all of the equations here. Now, hydrofluoric acid is a weak acid, so it only undergoes a partial ionization or dissociation. You may see it written out as dissociation or ionization. And this simply just means splitting up the acid into its different ions. And they will always be H3O+, which is known as the hydroxonium ion. And it will always form that plus the halide. Any that are strong acids will undergo a full ionization. So instead of the double-headed arrow we get for the reversible reactions, we just get a single-headed arrow. Hydrogen halides can also react with ammonia in order to form white ionic salts. And again, you'll have seen this back in GCSE. And it's specifically the reaction to form the ammonium chloride from ammonia and hydrogen chloride. And we can use this to demonstrate the diffusion of gases. So the ammonium chloride solid is going to form closer to the HCl because it is heavier than the NH3, so the NH3 can move further and faster. Now, you are not expected to know any of the reactions of fluorides and acetides because they do not necessarily follow the same trends. What you can do, though, as a potential exam question for Unit 2, is they may say that the trends are similar and ask you to make a prediction. Okay? Now, none of the last 5 slides that we've been looking at for the different other reactions, so the formation of the silver halide, the reaction with water, and the reaction with ammonia, none of these are redox reactions because my oxidation number has not changed. The halide has stayed at an oxidation number of -1. So please make sure that you can identify redox reactions using oxidation numbers because, again, that is a typical exam question in Unit 2. So let's have a look at a past paper question. This question is from the January 2019 paper. So iodine can be obtained from iodine compounds, such as potassium iodide, by the reaction with chlorine. So this is an example of a displacement reaction. We want to write the ionic equation for the formation of iodine by the addition of chlorine to aqueous potassium iodide. Now, what I'm going to do is I'm going to show you the full equation just to show you the working, and then I'll convert it to the ionic equation. If you do this in the exam, they will simply ignore the full equation as you're working, and they will mark only the ionic equation. So we are reacting potassium iodide, which is aqueous, to chlorine gas, and we are going to form potassium chloride, and we're going to form the iodine. Now, in this case, we're not required to have the state symbols. I've just written the state symbols just to help you visualize this a bit easier. Now, let's just check our balancing. Well, we need 2 of the potassium iodides, and we will make 2 of the chlorides. Now, hopefully what you can see is that this potassium ion on both sides has remained unchanged. So the potassium ion is a spectator ion. So we don't include that in the final equation. So all we want to be looking at is the iodide, the chlorine, forming the iodine and the chloride. So let's rewrite it underneath, but we're going to have two iodide ions reacting with chlorine gas, and we are going to form iodine solid, or I2, and we're going to form two chloride ions. This is your final ionic equation, and that's for 1 mark. Now, the colour of the iodine solution formed is a red-brown colour, and we want to extract the iodine from the aqueous solution using an organic solvent and then give the colour. So I did say that this is one that you should know for exams, and your best organic solvent to use typically is cyclohexane, but you can use any suitable liquid organic solvent. You cannot use an alcohol or any of the alkenes, but anything like cyclohexane, hexane, heptane, anything like that. And the colour for iodine is going to be purple. They will also accept pink, violet, or mauve. And there you can see the answer for the 2019 paper. Let's look at the 2018 paper. This is a slightly longer question, and it's all about the chemistry of group 7. So silver nitrate solution is added to an aqueous solution containing two different halide ions, and we get a mixture of two precipitates, A and B. When concentrated ammonia solution is then added, precipitate A remains and precipitate B dissolves completely. So identify by name or formula the halide ion in A. Well, the fact that when we add the concentrated ammonia, precipitate A does not dissolve, that can only be iodide or I-. Notice that it specifically says the halide ion. If you write iodine, you will not get the mark because that is the halogen. Identify by name or formula one possible halide in B. Well, we see that B is going to dissolve completely in the concentrated, so there are two possible answers here. I'm going to give you both of them. It can either be chloride, which is Cl-, or bromide, which is Br-. Of course, you only have to write one of them, so you can select which one. It will also give you the mark if it says both. However, best way is to read the question and see that it only asks for one of them. Because if you write one that is correct and one that is wrong, you will lose the mark. So we want to write an ionic equation including state symbols for the formation of the precipitate. Well, you've been doing this since GCSE, and it is the reaction of the silver 1+ ion, which is always aqueous, with the iodide 1- ion, which is also aqueous, forming silver iodide solid. And that gets you 2 marks. 1 mark for your species and 1 mark for your state symbols. So concentrated sulfuric acid is added to the potassium chloride, and the reaction occurs that gives steamy fumes. Give the formula of the steamy fumes. So we're getting this potential reducing reaction happening here, but remember, because it's potassium chloride, it's the H2SO4 is only going to act as an acid in this case rather than as an oxidizing agent. So the steamy fumes that are going to be formed is HCl. Notice that it says the formula, so you cannot write hydrogen chloride, and you don't have to provide a state symbol, but you can put it as a gas. And we want to write the equation for this reaction, so we're going to get H2SO4 plus KCl is going to give us 2 possible outcomes. We could get KHSO4 plus HCl, or they will also accept K2SO4 plus 2HCl. And if you do it that way, then if I change that, you're going to have H2SO4 plus 2 potassium chlorides. Any one of those would be acceptable. So remember, in this case, it's going to be just the HCl that is being formed. We're not getting a redox reaction happening here. So when concentrated sulfuric acid is added to potassium bromide, now we get a redox reaction. And we get a mixture of products being formed, including the sulfur, in this case, as the only reduction product. We want to give the oxidation numbers of sulfur and sulfuric acid and sulfur dioxide. So we've got H2SO4. So remember from our oxidation number rules, hydrogen is going to be +1, and I have 2 of them, so that's going to be +2. Oxygen is always -2, and I have 4 of them, so that's going to be -8. It needs to balance out to 0, so if I have a -8 and a +2, that means that my sulfur must be +6. So for sulfuric acid, it is +6. For the sulfur dioxide, for SO2, oxygen is always -2. We have 2 of them, which gives me -4. So that must mean that my sulfur in this case is +4. And then we want to complete the ionic equation for the redox reaction. So we have the H2SO4 reacting with the certain number of hydrogen ions and a certain number of bromide ions, and we're going to form 2 products plus water. So our 2 products in this case is going to be bromine, Br2, and our only reduction product is the sulfur dioxide that is being formed, which is SO2. And that gets you the first mark, and the second mark is simply to balance it. So if I make a bromine molecule, I must have 2 bromide ions, and I'm also going to make 2 waters, and I'm reacting 2 hydrogen ions, because remember the H plus and the Br minus is actually the hydrogen bromide, so they should be in a 1-to-1 ratio. And that gets you your 2 marks. When concentrated sulfuric acid is added to the potassium iodide, again we get this redox reaction and we get 2 additional reduction products being formed other than the sulfur dioxide. So we make the sulfur dioxide and we get 2 more. We want to identify what both of them are and then identify an observation that indicates the presence of these. So this is going back to that table that we looked at a while ago. And so we make sulfur dioxide. We're also going to make sulfur, or you can write the formula as S, and this is going to be a yellow solid, and you have to be specific that it is a solid. You can also write precipitate. And the second reduction product is going to be H2S, or hydrogen sulfide. Again, name or formula is acceptable, and that's going to give you a smell of rotten eggs. Remember, it is a colourless gas, so you can't say that you're going to see the gas, but you do smell the gas. And there's the mark scheme if you want to have a check for those answers. Now that's everything for topic 8C, the inorganic chemistry of group 7. Hopefully this has all made sense. Some of it can be quite tricky, particularly the reactions with the halides and sulfuric acids. So be sure to practice writing out these ionic equations and make sure to read through the textbook and try some of the questions in there. As always, if you have any questions, please feel free to leave a comment below, and we hope to see you back on the channel soon.